Alright, I like to go over the quiz along with posting things on D2L. It does help, I think, sometimes to see it drawn out, so bear with me. So for the first question, it was about OF3 plus 1, drawing this Lewis dot structure. This would be the equivalent of hydronium if you replaced this with hydrogen. It's just the convention is a little different. That it would be H3O plus. Now, if we count up electrons, again it always starts here, oxygen has 6 valence electrons. Fluorine, there are 3 of them, so it's going to be 7 times 3, so that's 21, so that's 6 over. But we have to take into consideration the charge. This is a polyatomic ion. Positive charge means we remove an electron. So in my count, I would subtract 1. So I'm going to have a grand total of 26 electrons to work with. Again, this is something that is absolutely imperative, but very easy to forget the fundamentals. If you don't count up the proper number of valence electrons, you'll try and make this molecule with 6 electrons or 4 electrons or something. In other words, you'll be basically stuck, but without any way of moving forward, because if you don't have this, you're not going anywhere. So, oxygen was listed as the central atom. For a Lewis dot structure, you do not have to represent the 3-dimensional structure. So I could put these fluorines around in 120 degrees, or I'm kind of drawing it now as if they were at 90 degrees. Obviously, when we're finished, it's going to be, electronically, would actually be a tetrahedral. But again, for a Lewis dot structure, we don't care about that. That's where Vesper structures come in. First things first, we need to make chemical bonds. So 2, 4, 6 electrons. There are a couple approaches you can have. I always take the approach of, after I've put all the bonds together, I start from the outside, the terminal atoms in this case, and just put in lone pairs till they get an octet. If I need to rearrange for double bonds, then I'll do that later. So each fluorine needs an octet. 2, 4, 6, right? So 2, 4, 6, 8. We have an octet. We do the same for the other 2. So 2, 4, 6. So I've used a total of 12 electrons, 14, 16, 18. So 6 times 3 is 18 electrons. Well, now we have 2 electrons left over. If you fall into this trap, if you say, well, I got 2 electrons, double bonds are cool. If I put a double bond here, well, fluorine has just violated the octet rule. And obviously the same is for everything else. There's also formal charge reasons why you can't do that, but without a doubt, that's gonna be the end of it. So these last 2 electrons I put in as a lone pair on oxygen. The oxygen now obeys the octet rule. 2, 4, 6, 8. I did not ask you to calculate formal charges in this particular molecule, but if you did, oxygen would have a positive 1 formal charge, and the fluorines would be 0. Right? Formal charge, it's the number of electrons that it has as a neutral atom. We count 1/2 of each chemical bond, so 1, 2, 3, 4, 5, because it owns the 2 electrons in the lone pair. So 6 minus 5, excuse me, is going to be positive 1. Well, this molecule has a plus 1 charge. That makes sense. And just for completeness, the formal charge for the fluorines, 7. Again, we start with 7 valence electrons. 2, 4, 6, 7, right? 1/2 of the bond. 7 minus 7, of course, is going to give me 0. I did not ask for formal charge in this particular molecule. However, it's not a bad idea to go ahead and calculate it for 2 reasons. One, Self-consistency. The molecule is an overall +1 charge. This is a polyatomic molecule. That means something has to have a +1 charge, or some set of charges that when you sum them together, you get +1. Could have been, +2 and a -1, and that would still work. So that's self-consistent. Oxygen is +1, the fluorines are 0. The other thing is charge separation. If you try to do something with the double bonds, putting a double bond here, along with an octet rule violation, now you're starting to change the formal charge of the fluorine from 0 to -1, and that should also be a warning that if you start inducing too much formal charge, especially in this case the wrong one, I think you would end up with, let me do the math, yeah, you would end up with a +2 charge on oxygen and a -1 on the fluorine. Formal charges are allowed, but you try to minimize them when possible. In other words, if you have two possibilities that do not violate the octet rule, or octet rule violations are allowed, then you minimize the formal charge. So in this case, double bond to fluorine, octet rule means in this case that's not going to happen anyway, and your formal charges would increase, which is also unfavorable. So this is something that, if you don't go back and do this analysis, you can fall into that trap. But again, in this case, all I asked for was the Lewis dot structure. I will be giving us more complicated molecules on more examples where calculating formal charge is necessary. All right, so for problem number 2 on the quiz, the question was, what is the orbital hybridization of carbon in CO2? What is orbital hybridization? Well, again, we have to go back to some of the first principles of bonding, of looking at combinations of S, P, I'm just going to put an X there, of what orbitals are used between atoms to form those chemical bonds. Now again, valence bond theory is an aspect of chemical bonding where in Lewis theory we're all focused about the octet rule. As we progress a little bit into more of the details, more of a rigorous treatment, we actually start looking at, well, if an atom has s orbitals and p orbitals, how do they combine between atoms to form chemical bonds? So I'm going to draw the Lewis dot structure first, and I'm not going to go into this in very rigorous detail. In other words, I'm not going to actually show the orbitals. When we have double bonds in a system, then what that means is we have a combination of s orbitals and p orbitals. However, just kind of as an aside, if I have methane, before I come back to this, well, methane has 4 sigma bonds, 4 single chemical bonds. So each one of those chemical bonds is from a hybrid orbital, S, Px, Py, Pz, the 4 orbitals that carbon has available for chemical bonding. So all 4 of those orbitals, S, Px, Py, Pz, are hybridized, making our hybrid orbitals, so sp3 hybridization. However, when we start putting in chemical bonds that, double bonds into our system, we do not hybridize for chemical bonds that are called pi bonds, indirect bonding. So, for carbon in carbon dioxide, it has 2 chemical bonds that we would call sigma, which are direct, and 2 chemical bonds which are pi, the double bond. So it's going to be sp hybridization. The overlap that makes up our double bond is from the non-hybridized p orbitals interacting with a non-hybridized p orbital. That would be on the oxygen. Another way of writing this out from a nomenclature point of view is that the bonding between carbon and oxygen, we've got a sigma bond and a pi bond. We are right now in the process of going through molecular orbital theory, where we're going to look in a much more rigorous way at how orbitals overlap for chemical bonding. So right now I'm not going to write this out, but we will be going back and reinvestigating these systems in a very rigorous manner. So again, kind of close the loop on this. If I have a system, so I gave methane as an example. If we have ethene, where now we've got a double bond between the carbons, each carbon is now sp2 hybridized. We would have 1, 2, 3 sigma bonds, and there would be that sigma bond and a pi bond between the two carbon atoms in this molecule. And I'm going to squeeze this over here. Sorry about this, I'm making this up as I go along. If we have ethyne, which we call acetylene, now we have a triple bond. So this would be 1 sigma bond and 2 pi bonds. So that means between the carbons, we've got 2 pi bonds, but remember we've got the hydrogen here. So each carbon is only sp hybridized, which would be the same as this carbon. So the thing is, saying sp hybridization always corresponds to a bond order, well, we can see that's not true, because it depends on what you're attached to. So here we have 2 double bonds, sp hybridization. Here we have 1 triple bond, and each carbon ends up with the same hybridization. The number of pi bonds and sigma bonds, the total adds up, but the distribution is different. So going back to this, the answer would be sp hybridization. As we move into fun stuff, where we start looking at violations of the octet rule, well, if I have 5 chemical bonds, sp3 is 4 chemical bonds. So we have to have an orbital hybridization of sp3d. Right? In most cases, when you're talking about Lewis structures and so forth, you don't violate the octet rule. You don't have what's called the expanded octet. This course, obviously, we're going to throw all those rules out the window in many cases. So we'll see that, yes, we will have to look at the orbital interaction of the sp and d orbital sets as we go forward. But again, just to reiterate, for this particular problem, sp hybridization. All right, for problem number 3, which of the following species is paramagnetic? The answer is carbon. I'm not going to go through the other examples, the other choices. You can go through them yourself once you see how you're supposed to go through them, if you didn't get this right. Carbon as an atom, its electron configuration, 1s2, 2s2, 2p2. All right. Again, nothing fancy here. I've got my periodic table. 1s1, 1s2 gets me helium. 2s2 is lithium and beryllium, and then p1 is 2p1 is boron, 2p2 is carbon. Now when you look at this, well, I asked for which species is paramagnetic. Paramagnetic does not mean even or odd necessarily. If it's an odd combination, well, then it sticks out like a sore thumb. But you can also have an even number of electrons that are paramagnetic. How? Well, draw out the orbitals. I'm not going to draw these in terms of energy because I don't want to make it, I can move this a little higher. That's it. So this is not meant to show them by scale or anything. So 1s2, let me get a different color. So 2 electrons in the 1s, spin up, spin down. 2 electrons in the 2s, spin up, spin down. But now we have 2 electrons that go into the 2p. Again, going back to the basics of quantum mechanics. Pauli exclusion principle, Hund's rule, all that good stuff. When I put the electrons in here, there are rules that govern how we put electrons in. I skipped the off-bow principle. Again, all of these fundamental things, I'm not going to go over them right now. But when I have degenerate orbitals of the same energy, I put in the first electron in any orbital, in any configuration, spin up or spin down, it doesn't matter. However, now that I've chosen that I'm going spin up, the next electron goes into a separate orbital and with the same spin. Okay? The Hund's rule, maximizing spin. You have electronic repulsion of what moves them into the different orbital sets. So, by inspection, well, we can see 2 unpaired electrons, it is going to be paramagnetic. If you look at every other choice that was given, calcium, and I'm not going to, like I said, I'm not going to write these out, aluminum +3, neon, and sulfur 2-. If you look at each one of them and write out their electron configurations and do it graphically like I just did here, you will find that each one of them is diamagnetic. All the electrons are paired. So if this was carbon +2, then we would remove these 2 electrons and it would be diamagnetic as well. But again, for neutral carbon, it's going to be paramagnetic. Again, 2 unpaired electrons. And this is something that it's very easy to fall into the trap of forgetting what 1s1, 1s2, 2p2, and so forth, what these represent. Again, we could have up to 2p6, in which case we'd have 3p orbitals. Each one would have 2 electrons. That would be diamagnetic. The reason I harp on things like this is a ground state electron configuration of an atom. In molecular orbital theory, we will be taking these, combining them, and then making molecular orbital theories, orbital diagrams of molecules. So if you're having trouble with the atoms, or if you forget some of the rules for the atoms, you're just setting yourself up for failure on the molecular orbital diagrams for what I would consider to be a trivial reason. Again, this is something to review. All right, problem number 4 for the quiz. Which molecule is polar? Hydrogen. And here I did not give you the Lewis dot structure. That was something that you could have and probably should have drawn. Diatomic oxygen. CO2. I drew this one in the previous problem. HCl, and diatomic fluorine. I'll move the fluorine down a little bit so it stays more centered. Now, fluorine is the most electronegative element on the periodic table, but that's completely irrelevant in this case. When we're talking about polarity for a molecule, we're looking for symmetry. If fluorine is pulling, if one fluorine is pulling in this direction and one fluorine is pulling on this direction, and what I mean by pulling is, of course, on the electron pair that is being shared in the chemical bond, the net result is zero. So the dipole moment is zero. So by definition, we're not going to have a dipole moment. It's not going to be polar. And of course, you can do the same for each of these. Now again, with CO2, you might say, well, oxygen is more electronegative than carbon, but we have an oxygen pulling in this direction, an oxygen pulling in this direction, because the molecule is linear. So that also becomes dipole moment of zero. I'm ignoring hydrogen and oxygen because that should be obvious at this point. That again, because they're the same element, the single bond to the double bond is irrelevant as far as it's the same argument for fluorine, symmetrical. But HCl, well, chlorine, and I'm drawing this very exaggerated, has a much larger electronegativity than hydrogen, so that the shift of electrons is going to be towards the chlorine. So the chlorine will have a partial negative charge, and these colors, I'm just literally grabbing them so they don't actually mean anything. So the chlorine will have a partial negative charge, and therefore the hydrogen will have a partial positive. So the little squiggly thing is lowercase delta. So the answer, HCl is polar. Now again, in this case, you could have done it by inspection, but if you weren't comfortable, if you did feel like you were guessing, you need to draw the Lewis structures and then analyze it from a electronegativity point of view. Again, the way I teach it is in Chem 101, or general chemistry, is you think of it as a game of tug of war. If you have two identical people pulling on a rope in opposite directions, the net result is zero. They cancel each other out. But if you have somebody who's big and strong, somebody who's not as strong, there's going to be a shift. The stronger person is going to pull the rope more towards them. In using that analogy, if they remove the entire rope from that person, then the charges would be, in this case, +1 and -1. In other words, that's ionic bonding. But in polar covalent bonding, there's a distortion in the distribution of electrons. Again, the electron density is moved more towards the chlorine, but not so much that it makes this chemical bond ionic in this situation. That's how we get partial charges. And in the case of carbon dioxide, because of the symmetry, yes, oxygen is more electronegative, so this one is pulling on the carbon that way, but this oxygen is pulling in the exact same amount in the opposite direction. They cancel, so dipole moment of zero. Again, this symbol is mu, which is used for dipole. The larger the value of mu, the more polar the molecule. We will be getting into structure and symmetry concepts in Chapter 3 of this course. So what I'm talking about right now goes back to chemical bonding, Vesper. These molecules, with the exception of the CO2, actually don't have geometry because they're only two atoms. But we will be applying these type of symmetry arguments to more complicated molecules for polarity and other aspects of them. All right, in the last question, question number 5 on the quiz, I gave you this molecule. This molecule is benzene, and I asked what is the total number of sigma bonds and pi bonds in this molecule. Pi bonds are double or triple bonds. So I'm going to draw over these. So we would have pi bond here, pi bond here, and a pi bond here. So we would have a total, put this off to the side, we have a total of 3 pi bonds in this system. This particular molecule, benzene, if you've had organic chemistry, you know about aromatic molecules and so forth. I could rotate the bonds from here to here and so forth and get the same result. We'll talk about the concept of delocalized electrons in more detail. That's actually something that brings us into molecular orbital theory. So 3 pi bonds, Sigma bonds are our single bonds, and this is something that it's very easy to forget. Well, the hydrogens are bound to carbon. So we're going to have 1, 2, 3, 4, 5, 6 sigma bonds from the hydrogen to carbon chemical bond. But we're also going to have 1, 2, 3, 4, 5, 6 sigma bonds between the carbon atoms themselves. So we have a total of 12 sigma bonds. So symbol for pi, sigma. Either way, you'll see them written out either way as the symbol, or written it out that way. And again, this is something that as we go through chemical bonding, recognizing the overlap between s and p orbitals, and is it a sigma interaction, a direct interaction, or is it pi? Is it some type of interaction? In this case, this molecule is planar, so we have interactions above and below the ring. And we will, like I said, be getting into many more interactions between s-p orbitals and d orbitals, and that's one of the reasons why I'm kind of going back and hitting some of these Gen Chem topics, because we're going to go to a new orbital set. So you've had experience with s and p orbitals, but when we start adding in the d orbitals, that's going to be, I'm sure, a lot of fun.